Hello, my name is Dave Gorman, and I teach 7th graders about science at Cedar Bluff Middle School. Our lesson today is Science Grade Level 7, Activity 4 for the summer. Remember, our activities and handouts can be found under the Student Resources tab on the Knox County Schools website at www.knoxschools.org. Be sure to show us what you learned and tweet us at KCS Science. We'd love to hear from you. If this video is hard to understand, you can turn on the closed captions if available. You could also adjust the playback to slow down the video. You could consider watching short clips and then pause, listen, and watch again, or ask someone in your home to watch the video with you. Stop it frequently and talk to your partner about what you heard and understood. Our activity today asks this question: how does human activity impact global climate? Our standard says we are to engage in a scientific argument through graphing and translating data regarding human activity and climate. We have 3 learning targets today. We want to be able to define greenhouse gases, fossil fuels, and global warming. Second, we want to describe human impact on climate. And then using a graph, we want to be able to predict how changes in human impact or human activity will impact that global climate. We have some vocabulary words that we want to work on. We'll be using these today. Our first one is greenhouse gases. These are gases in the atmosphere that trap energy. Our common greenhouse gases include things like carbon dioxide, methane, nitrous oxide, and water vapor, and a few others. We're also going to be talking about fossil fuels. You've heard about these perhaps. These are things like coal and oil, or natural gas. It forms over millions of years from the remains of ancient organisms. We burn these things to release the energy that's trapped inside. And then finally, global warming. This is a gradual increase in the average temperature of the atmosphere. It's thought to be caused by an increase in greenhouse gases, which are created by human activities. Okay? And again, you can pause this and come back and read these definitions again if you need to. All right. Now, you have a worksheet. Go ahead and let's take that out. It asks a couple of questions, and we'll give you some time to answer those. And for this, I am going to ask you to go ahead and pause the video to answer these 3 questions. Okay? Go ahead and pause it now. When you're done, you can start it back up. Okay, so we asked you to write down some things that you now know about greenhouse gases. Perhaps you didn't know what some examples might be. We're going to learn here in a few moments why they're called greenhouse gases if you don't know that. We also asked you to write down some things that we know about fossil fuels, where they're formed or what are some types, what are they used for, and then what does global warming mean? Well, let's continue and we'll figure that out, okay? But first off, let's get some background information. We hopefully have learned about this in the past, but let's make sure we remember about the atmospheric composition or the makeup of our atmosphere, okay? 78%, the biggest portion of our atmosphere, is made up of a gas called nitrogen, okay? 78% of our atmosphere is nitrogen, not oxygen, not carbon dioxide, the gases that we hear the most about. Now, 21% of our atmosphere is oxygen, which is great. Living things need oxygen, okay? But if you add 78% for the nitrogen and 21% for the oxygen, what do you get? 99% of our atmosphere is those 2 gases. Doesn't leave much room for argon, which is pretty close to 1%. And then carbon dioxide and some other gases I'm going to talk about in a moment. They make up less than 0.1%. Not much of our atmosphere. But those things do cause big problems. These other gases that are found in the Earth's atmosphere include very small or trace amounts of neon, helium, methane, krypton, hydrogen, xenon, ozone, iodine, carbon monoxide, nitrous oxide, and ammonia. Okay. Lower altitudes also have quantities of water vapor, clouds, things like that. Okay, so it's common stuff, a lot of these. All right, just to make sure, if we're going to talk about greenhouse gases, we should know what a greenhouse is. Here's a picture of a greenhouse. A lot of vegetation, and those look like it's plastic over top. It's a glass or plastic enclosed growing space that traps heat from the sun to help plants grow year-round. And you can imagine if you walked into that greenhouse, it probably is warmer inside there than it is outside the greenhouse. Okay, that heat gets trapped, the plastic or glass will keep it inside. Because energy from the sun is captured, the air temperature inside will be warmer than the air temperature outside the greenhouse. Okay, and plants need that warmth, and it helps them grow. So what is the greenhouse effect? Well, here's a diagram that gives us some ideas, okay? We can see two big yellow arrows coming from the sun, and that shows heat from the sun that's moving in and striking the earth. And some of it is reflecting back off the earth and into the atmosphere. That's a great thing, okay? It reaches the earth, it warms up the surface. Some of it is reflected back towards space, easily passing through two gases that are common, nitrogen and oxygen, okay? They don't trap the heat. However, when this heat makes contact with gases that do trap the heat, carbon dioxide, methane, ozone, water vapor, and nitrous oxide, like we talked about, this heat is trapped. It causes these gas molecules to vibrate and heat up. They store the heat, they trap the heat. So you can see those red arrows on the map radiating off the land masses, in this case North America, and then bouncing off the atmosphere. You can see some water vapor in the form of clouds, and then some of those other gases like carbon dioxide. Okay, that heat is trapped, it can't get out, so it's going to work like a blanket, cover up the earth, and cause temperatures to rise. All right, some review on fossil fuels, just what they are, and we mentioned coal, natural gas, and fuel oil. These things are created from the remains of dead plants and animals, okay? The thing about it is, it takes millions of years for these things to form, okay? They're considered non-renewable resources because it takes so long for those things to form. They form underground, lots of heat, lots of pressure to create them over time. And then we have to dig down, usually dig in wells or in mines to bring these things out. We get the heat through combustion, so we burn coal, we burn the oil in the form of gasoline or fuel oil, things like that we use to heat our house. Okay? The energy is released through burning. Unfortunately, when we burn those fossil fuels like gasoline, this could be the result. Would you want to breathe in that? Take a look at that picture. That is smoke and exhaust and smog and air quality very, very bad in that area. We use coal, and here's a picture of a power plant in China, and they're burning coal, and you can see the smokestacks are all producing a lot of smoke and releasing greenhouse gases into the atmosphere. They're burning that coal to turn generators to create electricity. So it is necessary that we have electricity, but this type of burning really puts a lot of greenhouse gases into our atmosphere. Okay, so you might ask about these greenhouse gases. Again, what percentage are these different gases of the whole, and where do they come from? So let's take a look at this graph, okay? The types of emissions. When we emit something, we release it, okay? Light can be emitted from a flashlight. Light is emitted from the sun, okay? Where do these emissions come from? So carbon dioxide, 82% of all of these greenhouse gases are carbon dioxide. And again, carbon dioxide makes up just a very, very small slice of our atmosphere. But most of the greenhouse gases are carbon dioxide. Methane Nitrous oxide make up the next two pieces. And then something called HFCs and PFCs, hydrofluorocarbons. These are things that are propellants and used in air conditioning, and they get released in the atmosphere, and they can really cause some problems for us. The sources of these emissions, you can see that the biggest piece is in the generation of electric power. We saw a slide a few moments ago that showed coal being burned to run generators. The production of electric power uses and produces a lot of particulates in the air and carbon dioxide in particular. Transportation, driving, flying, these ways that we get from one place to another that don't involve bicycles or electric vehicles or walking. These things all release a lot of carbon dioxide into the atmosphere. Industry, we have companies that use a lot of power to create things, to make things, to build things, okay? But as a result, they're also releasing these chemicals, these gases into the air. Agriculture and farming, commercial, and then residential. These are some smaller pieces. But again, the biggest piece goes to the generation of electric power, okay? Well, let's move on. So another diagram showing something we've been talking about here. The natural greenhouse effect on the left side shows radiation from the sun, this heat from the sun hitting the earth. Some of it is going to be absorbed by the earth. Some of it is going to be re-radiated back up, strike the atmosphere. Some of it is going to strike the atmosphere and come back down. It's natural. It's not unusual. A lot of it will then escape into space. You can see the large arrow pointing back up towards space as energy is released. On the right side, however, we see what happens with greenhouse gases and what they can do. You've got CO2, which is carbon dioxide, of course, CH4, which is methane, N2O, which is nitrous oxide. These are greenhouse gases, and again, they form that insulating blanket around our atmosphere. So the sun heats up the earth, the heat strikes the earth, and then it reflects. It would go back out into space, except now it's trapped by this blanket, by this insulation, these greenhouse gases. And just like the picture of the greenhouse that showed clear plastic that was trapping heat, these greenhouse gases are going to maintain heat. And again, you can see that very small arrow leaving from the atmosphere back into space now on the right side. It says less heat escapes into space. So more of it is trapped. Human enhanced, human caused, okay? Our activities. So what are some impacts from global warming? And you can take your worksheet. This is at the bottom of the first page, question number 4. Some impacts, okay? And I'm going to give you a few moments to think about that. And I'm going to ask you to pause the video one more time. And after you've thought about this and come up with a couple of impacts, this is ways that global warming affects the Earth, then you go ahead and hit play and you can continue with the video. Okay, we've written down some things, and hopefully you came up with pollution, you came up with fossil fuels that are non-renewable, and let's talk about some more impacts. Here's one that's very, very serious. Sea level rising, okay? Well, we've got ice that's melting, we've got water that's heating up. As things heat up, they expand, okay? They take up more space. And so as a result, we can have oceans that suddenly the water expands and it hits shorelines, and low-lying coastal areas like we have a lot of in the eastern U.S. and along the Gulf Coast are going to be in danger. And maybe you've been to some of these places like Charleston or Myrtle Beach, which is nearby, down anywhere coastal Florida, maybe New Orleans, okay? And you can see the darker the color, the greater the effect of sea level rising, okay? Melting glaciers, pack ice, rising water temperatures all cause an increase in the amount of seawater, okay? Those things like we don't think of glaciers too much being along the coast of the U.S., okay? But the water's going to reach us, of course. The impact would be devastating. If we were to have a 6-meter rise in water in this area along the east coast of the U.S., along the Gulf Coast, that's 20 feet, okay? New Orleans, for example, would disappear. It's already below sea level, and now if we were to have that much water come in, look how dark those colors are. New Orleans would be gone, okay? All right, another big thing that happens is the loss of habitat. Habitat is where things live, where plants and animals live. And conditions hopefully exist where they get plenty of their needs met, they get plenty of sunlight, or there's plenty of food options and water and shelter for them to live, okay? But as rising temperatures cause ice to melt, things like reindeer, caribou, may have less places where they can live, okay? Sandhill cranes, which migrate up to Canada and they nest and raise their young up in Canada. They come back down to the U.S. and actually migrate to near Chattanooga, Tennessee. There's a flock of sandhill cranes there. Well, if temperatures are too warm in Canada, then the conditions may change and they're not able to successfully mate and raise their young up there. Puffins, this is a crazy looking shorebird, really cute looking. But they need conditions just right. They like cold water. They feed on fish. Well, if the water's warming up, there may be more competition for the fish, or there may be less fish to begin with because the water's too warm. Amphibians. Amphibians are an indicator species. They have very, very thin skin, very susceptible to changes in the climate. Okay, temperature goes up, then we may have less amphibians. Polar bears. Here's a bunch of polar bears that look like they're at a dump. They're not hunting for seals on pack ice like they normally would. Penguins, if they have less ice available, that means fewer places for them to nest, and lots of competitions. All right, so our increased ocean temperatures can cause unstable weather. We get more hurricanes, tornadoes. We can have a lot of rain in Tennessee as a result of this. More snowfall, glaciers that are retreating, melting, okay? Increased acidification of seawater. We don't think about that, but those gases have acid in them, and so when they strike the water, when they dissolve in the water, those chemicals then create more acidity in the water, and that reduces the viability for some species to be able to survive. Okay, so this is a picture of a huge hurricane. This is Hurricane Sandy, which devastated New Jersey and New York. Massive power in that storm a couple of years ago. There's a big piece of glacial ice that's sheaving or calving, releasing and breaking off. This is a picture of some bleached coral in the barrier reef down off the coast of Australia. Water temperatures got so high that all the organisms that live on the coral died, and that whole ecosystem is in danger of collapsing. All right, we'll go back to our worksheet and let's take a look at this graph. You have this picture, even though it says question 4, this is question 5. What does it show us? A couple of questions. Which country produced the greatest amount of carbon emission worldwide? Okay. And which country produced the least? So it does say the EU28, that stands for the European Union. That's a coalition of countries in Europe that cooperate and share resources. A lot of countries that don't individually use enough and create enough emissions are bonded together in that category for others, but those are not individual countries, so just ignore that, okay? Answer those 2 questions. Okay, and again, let's think about where this global warming is going, okay? As temperature heats up, where is it causing the most trouble, okay? Down to the lower right side of this graph, it shows our ice sheets. They're taking a bit of a hit, but not as much as glaciers and continents. Continents like North America are seeing an increase, 2.1% impact of all the global warming is affecting these land masses. Atmosphere heating up a little bit more, 2.3%, but the biggest part of our planet that's being affected by global warming is the oceans, okay? 93.4%. So again, as that water heats up, it's expanding, it's spreading out. And as that water spreads out, well, that's where you can get those sea level rising, that coastal flooding that we're talking about. Coastal flooding is not a problem for us in Tennessee. You know, we don't have to worry about that. We're not along the coast. But again, it is having the potential massive effect around the world and affecting our country as well. Okay, here's an interesting slide that shows crop yields. So these are corn and soybean, and our graph moving from left to right in both cases shows a production of corn that was at 2 tons per hectare. Hectare is 100 meters by 100 meters. And our corn production was pretty good. As the temperature rose, however, the corn production dropped off. You can see the same thing happening with soybean, although it's not quite as dramatic a drop. Soybean production dropped as well as the temperature increased. And you can imagine that might be because as temperatures increase, there might be less water available. Maybe there were more insects that were thriving in greater temperatures, things that were causing predation and causing these crops not to produce as much. Okay, here's an interesting chart that shows changes in the amount of atmospheric CO2, or carbon dioxide, over the past 400,000 years, so even before recorded human history. Scientists can take ice core samples. They can test it for the amount of carbon dioxide present as that ice melts and get a window into time, okay? And so tracking back over 400,000 years, they can look at, again, parts per million, how much carbon dioxide was in the atmosphere. And if you look at that chart, well, it has its ups and downs, and these are natural occurring changes in the amount of carbon dioxide that was in the atmosphere, okay? It's neither high nor low, it's up and down. These natural cycles that might coincide with ice ages or things like that, okay? But then we notice on the far right side that at around 1950, when of course scientists were measuring this stuff, the increase kept on going up. And for the first time, we reached over 300 parts per million in 1950. It got close. I mean, if you look way back about 350,000 years ago, it was at that line. It never crossed that line, okay? At about 125,000 years ago or so, it got close again. But since 1950, what has that line done? It's gone to 300,000 or 300 parts per million and continued, okay? Our current level is at 400, so it's grown in 70 years. It's grown more than it has at any other time in history that we can see. What might cause that to occur? Well, population growth. Population growth is let's see, 2.6 billion people on Earth in 1950, and now we're at about 7.8 billion people who have to be fed, who have to go from one place to another. So, human impact, okay, causing atmospheric CO2 to rise, perhaps. All right, here's another chart that shows atmospheric CO2 in parts per million from 2010 to 2019. Take a look at that chart. We have a couple of questions for you to answer on your worksheet. In 2010, our atmospheric CO2 was right about 388 parts per million, okay? At the end of this chart, if you follow that orange line, we get all the way up to about 412 parts per million. So what does that change over time? Over 10 years, we went from 388 up to 412. So that's about 24 parts per million. At that rate of increase, what do you predict the atmospheric CO2 level to be in 2024? Well, how would we figure this out? In 10 years, we went up 24 parts per million. Well, that's pretty easy. 24 divided by 10 is 2.4. We're going to extrapolate or extend this thinking, okay? At this rate of increase, what do we predict the atmospheric CO2 to be in 2024? So 5 more years. Well, we figure that out by taking 5 and multiplying it by 2.4. And that gives us 12. So by 2024, we could expect our total to be approximately 424 parts per million, okay? Continuing to rise. We could stop it. We'd have to make some changes in the fossil fuels that we're using. Okay, here's another graph that shows the change over time in the amount of sea ice in the Arctic. This is in 5-year increments starting at about 1980, so going up to 2015. So starting 40 years ago, we have 35 years or so of data here. Where do you see the highest amount of ice? Well, look at that graph, find the highest spot. And it looks to me to be about 1996, okay? And we got almost up to 8 million square kilometers of sea ice. Okay, this is frozen ice in the Arctic. We hit that high spot, and then what's happened since? Well, we've been on a downward trajectory. We've been going down. We've had some ups, but we've definitely had some downs. Okay, what was the lowest spot that we got to? Well, right about 2012, and we got to just maybe a little bit more than 3.5 million square kilometers of ice. Okay, now it didn't stay there. It increased. It got up above 5, but as of 2015, it's gone back down. So, again, lots of ups and downs, but we've been on a pretty consistent downward trend for several years. Okay, so what are some alternatives? Okay, we got wind farms, solar panels, nuclear power, geothermal energy, capturing, utilizing the thermal energy that's in the earth, and then hydroelectric energy like dams. This is Norris Dam, just north of Knoxville. Okay, our final activity. We've gone over a lot of information, and this is the last question on page 4 of your worksheet, okay? You've seen the data that shows the effect of greenhouse gases. Despite this information, many people still burn fossil fuels at ever-increasing and unsustainable rates. So use the chart on page 4 to answer both of these questions. On the left side, what evidence presented to you today would you use to argue that humans need to reduce consumption of fossil fuels as soon as possible? And then on the right side, again, this is an argument. You're arguing with yourself, perhaps. What evidence would you use to argue that human impact on the environment is overstated and that climate change is the result of natural and not human factors? So answer both of those questions. Compare those charts. Go back and look at any of them that you need to. And think for yourself. What do you see? What are the trends? Good luck, and thanks for watching. And again, let us hear from you. Tell us about what you've done, what you've learned, what you think, and tweet us at KCS Science. I'm Dave Gorman, signing off.